So finite state machines, okay, finite automata, also called finite state machines. Now, why it is called an automata? What is the reason? I think I have discussed this before. Can anybody remember? Can anybody tell me? And why finite? What are the reasons for these two words, finite and automata?
Ma'am, finite because there are only limited number of states a system
Finite
can.
number of states, not limited. Say, use the proper terms because finite here is important. It could be a very large number, but if it is still finite, then that is good enough. Okay. An automata, yes? Why automata? Or automate? Automata is actually a plural term. The singular of this is automaton, T-O-N. Okay. So automaton means it keeps on working automatically without external or manual intervention. Okay. So that's the reason. Okay. So now this you already know. They are a finite collection of states with transition rules. These transitions are represented by arrows, as you know, okay, which take you from one state to another. So this is one way of representing a system which goes through several states. Okay. Now this system could be a sequential switching circuits or sequential circuits. Why switching? Because flip-flops are usually called switching circuits. Okay, switching circuits is a very old, let's say it's not used much anymore, but switching circuits is an old term for your state machines, state circuits, or even logical circuits. Okay, so sequential circuits where the state is the setting of the internal bits. These internal bits, you know, they are stored in your memory elements or flip-flops. So that is where the term finite state machine comes from, and that is, you can say, one of the original applications or one of the original representations. But finite automata or finite state machines can also be used to represent other things. Okay. In fact, not just hardware, but also software can largely be modeled by finite automata, where the software also goes through various states, and this modeling by finite automata is used for checking the correctness of softwares, hardwares, or hardware software co-engineered systems, etc. Okay, so it's a very powerful model of representing any system that goes through states, provided, of course, these states are finite in number. And usually if it is small in number, very large number of states, then we have to look for other more efficient methods. So how do you represent finite automata? Typically in a graphical form. It's nodes and arcs. Nodes represent states, arcs represent transitions, and labels on arcs tell us the conditions under which this transition will happen. Okay, so this is old hat. Now here is an example which is not a sequential circuit as you have been familiar with. So this you can think of it as a recognition system. Okay, so what we are doing is we have got a stream of characters. These characters could be the text which is stored in a file. It could be anything. Okay, now we are trying to recognize what are these words ending in ing. Okay, as you can see, singing, dancing, etc. So this part, this recognition of the substring ing, this also we can represent in the form of a finite state machine. So what are the various states that would be? The first is when we have seen nothing. The second case would be when we have seen an I. When you see an I, you know that it's possibly the beginning of the substring which you are looking for. So you wait for an N. If you see an N, you go to saw, this third state which says saw IN, that is a substring of ing, and the final is saw ing, which is a final state. You remember final states or accepting states of finite automata. Okay, so this concentric ring around the state represents the final state. It can be called a final state, it can be called an accepting state, whatever. Okay, so these are this is the path you would follow when you're seeing ing. But what happens if you see some other character in between? Say suppose after I you do not see n. Okay, then what would you do? If you see another I, maybe the second I is the beginning of ing, so you stay in the same state. But if you see anything other than I or n, then you go back to the beginning. That means no, this particular substring is not the one which you're looking for. Okay, similarly, after from this third state. Okay, so this would represent the transitions which you would have to take. This you can say it is a pattern recognition system. Okay, so it's a pattern recognizer. And what do you think is the output of such a system? What is the output of a finite state machine? Can anybody tell me? Since you are not really new to finite state machines, you already have seen finite automata, finite state machines before. So what do you feel is the final output of a finite state machine? What is the output?
Ma'am, either 0 or 1.
0 or 1, but what do they represent? You're not wrong, but what exactly do you mean by 0 or 1? Do you say true or false?
If it's successful, then returns 1. If fails, then 0.
Okay, so you might say it is success or failure. I would say it is like accept or reject. Okay, so it is, you are absolutely right. Of course, it is either accept, reject, or success, failure, or true, false, whatever. It's a binary output. Okay, so say you have a continuous stream of inputs and you're trying to recognize the substring ing. Whenever you are successful in recognizing ing, you would end up in a final state. And be ending up in a final state, or rather being in a final state, is signals accept. Okay, then maybe if the string continues, you could go back. Okay, so there are two kinds of finite automata. One is where you begin and you end up in a final state. That is why it's called final. That means you stop there. Or else there is something called a bushy automata. Bushy automata is, just a minute, let me start the. Okay, so this is bushy automata, which is an automata which takes a continuous stream. So a bushy automata is one which goes on and on. As long as there is input coming, it will go on functioning. So in that case, this final state, instead of final state, we call it an accepting state. So every time you enter an accepting state, that part of the substring you accept as the recognized substring. So please remember, for any such finite automata, the output is actually a binary stream again, either 0, 1, accept, reject, true, false, whatever. Okay. Now, you have seen various situations which you might code using finite state machines. But if you had to write it in software, how would you write? This is very interesting because even when you design hardware, as you might already have realized, that even hardware is nowadays designed using HDLs, okay? Hardware description languages, which are very much like your programming languages like C. Okay, so if I had to design a sequential circuit, how would I write the code for it? Okay, so a sequential circuit, you can always represent its behavior using a finite state machine. In that case, you would have to write the code something like this. Okay, initialize the start state, then loop through the strings one character at a time, and you have a switch statement. For example, here you have several outgoing loops. You can see there's one outgoing transitions. This is one here, and one going backwards. So you might have to put in a switch statement with various cases for various inputs where you would go. Okay, and finally, when you end up in a final state, you write an accept. So this is basically the pseudocode of that you would have to code. And in Java, for example, your code would look like this. See, you have the switch case, okay, and depending on which character you are seeing, you can either go to this or that. And finally, so this is the final state. So what would be the output? The output would be something like accept or reject. And maybe if this entire thing, if you put in a loop, then you can turn it into, as I said, a bushy automata, and it can go on and on. Okay, so this is typically how you might code a finite state machine. Okay, now let's take a look at several finite automata so that you get an idea of what finite automata can do. So here is a very simple finite automata which you can see accepts a certain type of strings. What are the strings it will accept? Now the strings that this finite automata will take as input are strings of A and B. The two input characters in these strings are A and B. Okay, just as in case of binary strings, you have strings of 0 and 1. Here it's a case of A and B. And it doesn't matter how many B's you see. When you see exactly two A's, you accept the string. Okay, and once you have accepted also, after that also you can go on and on, doesn't matter. But two A's, when you have, if the string contains two A's, they don't even have to be consecutive. They can be B's in between. This loop is there. Suppose I remove this loop. Okay, if I remove this loop, can you see which loop I'm referring to?
Yes, ma'am.
Okay. So this particular loop I want to remove. Then how will the strings which I accept change? What kind of strings will I be accepting now?
Ma'am, only strings of A's.
No,
Just A. Just A with B at the end, ma'am.
no, that's also not correct. Be more specific, be more, let's say, to the point. Now, just look at this picture and the arc which I have circled, you think it is not there. I have rubbed it out. Then what will that finite
Ma'am, that
automata?
specific arc only. Ma'am, only that specific arc or
Only
of
that
the.
arc, the one which I
Oh,
have circled. Can you see the red circle around the arc?
yes, ma'am. Yes, ma'am.
Okay,
Yes,
I
ma'am.
have removed it. Okay, let me see if I can play around with the ink tool and some more. Okay, it's not going. This part is not going. Anyway, whatever. So this portion is not there. So what does the remaining part? The remaining part of the finite state machine, what kind of strings will it accept? Will you accept a string such as BAA? Will you accept this string? Where will it go? BAA. Can you see that?
It will go to the final state.
It will go to the final state, so it will accept this. Now, suppose I write BABA, this string. Okay, where will it
Ma'am,
go?
it's consecutive A's. Ma'am, it will only accept consecutive A's, ma'am.
Yes, that is right. So this string now will not be accepted because B is all right. You are still in the same start state. But then A, after that, B, remember this arc is not there. So when you see B, you do not know where to go. Okay, there is no path for you in this automata to a final state. So it will not accept this string. So BAA is now accepted. BA is not accepted. Is this clear? Okay.
Ma'am, if
So
there is, ma'am, I have a doubt. Like
yes.
in this case, we removed the B from the second state. So will it be a valid automata or invalid automata?
Why should it not be valid? It is still a set of nodes with transitions, okay? And you have conditions on the arcs, which tell you when the transition will happen. So basically, this part is not there, okay? I have deleted this. The rest of the automata remains exactly the same. So why should it not be the valid automata? No, why do you feel that it might not be a valid automata? Can you tell me? Then maybe I'll clear your doubt.
Ma'am, because after BA, when we encounter the second B, it does not know where to go.
BABA. Okay. See, when it encounters the second B and does not know where to go, that means it cannot find a path to some accepting state. It means this particular string is not accepted. Remember, we are doing accept and reject. So basically, this finite automata is a checker, is a kind of checker. So you are defining what is called a language. That means a set of strings. So what kind of strings will be accepted by this finite automata now? So if you have to put it in English like language, I would say all those strings composed of the characters B and A in which you have two consecutive A's. If this substring is embedded anywhere in your string, then that particular string will be accepted by the finite automata. Okay? This AA has to be accepted. There has to be a consecutive, two consecutive A's. You should not have something like two A's with some other character in between. The A's have to be consecutive. If you have a set of consecutive A's in your string, of course, after that, you might accept any number of B's or any number of A's. For example, if I have a string like, say, A, B, A, B, A, B, 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 A, whatever. Will this string now be accepted? This string which I have underlined, will it be accepted? Somebody please tell me. What do you think?
No.
No, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes or no?
Yes, ma'am.
It will be accepted.
Yes,
Yes,
actually it will be accepted. Why? Because the first two A's, they will take you to the final state. Okay. After that, you can keep on seeing B's, you can keep on seeing A, and after that, you can keep on seeing any number of A's and B's. You will be looping here. It doesn't matter. But once you have accepted, once you have reached an accepting state, okay, so this part has already been accepted. If this had been your string, so you would flag as accept after this point. At this point itself, you will say, yes, it is accepted. Okay. Do you understand what I'm saying? So, but if you think of this entire string as one string and the whole thing has to be accepted, then of course, since you are ending up, say this is part is B, since you are ending up in a not accepting state, you will say this whole string is not accepted, but this substring part is going to be accepted. So you will be passing through the accept once. Is this clear? Okay. So if we have to put in English like language, so this.
Hello.
Yes.
Ma'am, the third state is the accepting state, right? Where we get
Yes.
two A's. So
Mm-hmm.
after the accepting state, when we get another A, why we move away from the accepting state? But because the string is already accepted, it has two A's already.
Yes, it is on two A's already. In fact, if it has something like A, suppose B, A, B, 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 it is still in the accepting state, isn't it?
So ma'am,
It is still in the
after we
yes.
receive an A, when we are already in the accepting state, then we
Yes.
should go back to the accepting state, right? We are moving forward to the fourth one.
This is because what this finite state machine says is that once you have sort of transitioned through an accepting state, the entire string is going to be accepted, whatever comes after it. Okay. So if you say that I will only accept strings in which A's always come in pairs, then what you would have done, for instead of this arc, you might put an arc here on A. Okay, suppose instead of this is now going to be I have actually messed it up a great deal. So now my finite state machine does not have this fourth state, and it has only these three states. This is the accepting state. So I am saying that now I will accept strings in which the A's come in pairs only. Okay, the A's have to come in pairs. Then this would be the finite state machine. This arc actually also would be there. This B is there. Okay. So, I'm sorry, this will not be there. If it is there, A's will not be in pairs. So this, you can start with any number of B's, 2 A's accepted. You can see any number of B's, but the moment you see an A, that A has to be in pairs. A, accepted. Again, you keep on seeing B's. As long as you see B's, you are still accepting the string. Then again, when you see an A, you come back here, and then you must see another A for that part of the string to be accepted. Okay. Now here, since if you are moving away, what this means is, basically we want that the string should have these 2 A's. After that, it does not matter what it has. So any string which has 2 or more A's will be accepted by this machine. Do you understand what I'm saying?
Yes, ma'am.
Is this clear now? So by minor changes in the design of your automata, you can actually change the language which you are accepting, the category of strings which you are accepting. Is that clear? So that is called the language of a finite automata. Exactly those strings which will be accepted by this finite automata. Is that clear? Okay. So please remember, when you are describing the language of the finite automata, how would you, let's ignore this second part. So how would you describe the language accepted by this finite automata? So strings made up of A's and B's, very important. If you see a C or D here, you will not know where to go. So those strings are not going to be accepted. Okay. So only strings made up of A's and B's, in which the A's come in pairs. Is that correct? Is there any other string which will end up in a final state? No. If there is such a string, then this language description is not correct. You will have to describe the language differently. So by minor changes in your automata, you can actually change the language accepted by that automata. Okay. I think we should move ahead of this slide. Let's see several other examples. So the next slide is also an example, I think. Okay. So at least 2 B's. Here it says at least 2 B's. And you can see it is something very similar. Instead of the A's and B's have been interchanged. Okay. Now, here, what it says is all those strings which have exactly 2 A's and at least 2 B's. Okay, so this is actually, you can say, a product automata of the previous 2 automatas that were given here. Okay, exactly 2 A's and at least 2 B's. These 2 automatas, if you take a product, you will get this kind of automata. Now, this particular automata, I do not want to discuss now. When we do properties of context-free languages, I will make sure that I come back to this example and we'll see. Okay, but this automata now, what it says is, it is a combination of the 2 languages. So exactly 2 A's and at least 2 B's. The previous 2 automatas, if you take an intersection, you will get something like this. Okay, so again, I'm introducing some properties which we'll be discussing again in detail later. So here, the first automata, this one, the one on top. So this is all strings which contain the substring BA. Okay, so which contain the all strings of A's and B's which contain the substring BA. Right? And just below this here, you can see another automata which is just the opposite, which does not contain BA. Okay, so what we have done is, what was previously the accepting state, okay, this last state here. So what does this accepting state imply? All those strings which belong to this particular language. So what has been done here below, you can see that that accepting state has been made non-accepting. Okay, so and all the other states which were previously the rejecting states, mind you, okay, they have been made accepting states. So what does this mean? So all those strings which were previously being accepted will now be rejected, and all those strings which were previously being rejected will now be accepted. Okay, so this is actually a complementation. If you think of these strings as a set, okay, the complement of this set is being accepted by the second finite automata. Okay, so it is possible to accept some strings. It is possible to reject also, okay, by making a complement of this finite automata. If you do not exactly understand right now, please don't worry. Again, this is a property of finite automata. Not only finite automata, it is a property of the class of languages which are expressed by finite automata, which are called regular languages, okay, which we'll be discussing again in great detail later. So these are some of the examples. Yes.
What's the meaning of the concentric circle? Means
Concentric is accepting state or final state.
Means in the
Concentric,
second example,
yes.
the first, second, third, and fourth, all the first four are.
All of them are accepted. So see, note one thing here. This particular finite automata has a very interesting property. The property is that, remember, my strings are made up of only A's and B's. Okay, so whatever I get, either I will get as a input character A or I'll get a B, right? Whatever I get, I know exactly which is the next state to go to. That means this is a complete finite automata. It's a very good kind. It does not give you leave you in any kind of confusion regarding where you should go. So whether you get an A or a B from any state, you always have an outgoing transition on that character. Can you see that? So it's a complete finite automata. Can you all note this? You take any state. For example, let's take this third state here. Okay, if you get an A, you go back to the first state. If you get a B, you go here. Take this state here. If you get an A, you go here. If you get a B, you stay in the same state. So for every state, outgoing transitions are defined on all possible input characters. So it's a complete automata. Okay, it's not leaving any kind of confusion. It is completely specified. Is that clear?
Ma'am, you also said concentric means final state, but the first four states.
Yes, accepting. The first four are not accepting. You will only accept a state when you find the substring BA. Okay, you might get a long string. You might get a long string of A's and B's. You will keep on circulating in the first four states, and only when you see a BA, okay, you will end up in the final state. Is that clear?
Yes, ma'am.
Are you all convinced about that? So once you have seen BA, you end up in the final state, and then you continue in that final accepting state. That means BA should be embedded anywhere in the string. Then that string is acceptable to us. You see that? It does not have to be the last part of it. Does not have to be what is called the suffix. It can be embedded inside. It can be at the beginning. It can be anywhere. But we will accept any string which has this substring BA embedded in it. Okay, and here in the finite automata, which is at the bottom, this one, what we will do is we will again take all strings of A's and B's. Okay, as long as we do not see the substring BA, we will keep circulating in these first four states as before, because otherwise the automata is exactly the same as the one before, right? As long as we have not seen the substring BA, we will keep on circulating here. If BA do not ever appear, we will never go to this final state, this last state. Okay, so all those strings in which BA does not exist are going to be accepted, and any string which has BA embedded in it anywhere, at the beginning, at the end, in the middle, wherever, those strings will not be accepted, because you will be stuck in this final state here, this last state. I don't call it a final state, the last state here, which is a non-accepting state. It is no concentric circles are there. Can you see that now? So basically, these two finite automata, they have exactly the same structure. Only what is the accepting state here has been made the rejecting state here. All the rest are accepting states. So by this, by just inverting the sets of final accepting and non-accepting states, what we have done is we have defined two different sets of strings which are complements of each other. Okay, I think I'll stop here. We will discuss complementation in detail further on in the course. Okay, so let's see more examples. Okay, some general comments. What are the possible things that you can do using finite automata? You can, for example, recognize substrings. You can recognize sequences. You can do certain amount of counting, very small amount of counting, only counting which is finite and possible to represent in the finite automata. But unknown amount of counting which is not given, for example, any number which you represent using n, it can be anything. Okay, it can be a small number, say 2 or 3, it can be any big number also. But if you do not know the number in advance, you cannot represent. Okay, so modular counting, but this is this must be treated with a great deal of care. Okay, because the basic idea is that your finite automata cannot count, and some things are impossible with finite automata. Again, we will be discussing this again and again. You have to be able to recognize what are regular sets. All those languages or sets which can be represented by finite automata, they are called regular sets. Okay, for example, equal numbers of A's and B's. If you have to find strings which have who is that making a noise? Please don't make a noise in class. If you have to find strings which have equal numbers of A's and B's, then you have to keep a count of how many A's you have seen and how many B's you have seen. Okay, this is something a finite automata cannot do. Okay, more zeros and ones. Okay, again, you would require to keep a count of how many zeros you have seen and how many ones. This is again something a finite automata cannot do. Okay, so there are only very restricted type of patterns that a finite automata can check for. Okay, so these patterns, they are called regular languages. These patterns, they make up regular patterns, regular languages, and we use a formal way of representing these patterns that is called regular expression. Okay, so we will be discussing all these in detail in this course, and regular expressions, they define a class of languages which are called regular languages or regular sets. Okay, so all these automata that we discuss in this course, finite automata is only the first one, finite state machine of finite automata. Subsequently, we'll be discussing various different such languages, and you'll see how these languages, they keep on increasing in descriptive power, they keep on decreasing in descriptive power. Okay, and the largest language of all, which is called recursively enumerable language, is represented by something called a Turing machine. Okay, and a Turing machine is a formal model for everything that a computer can do, every kind of computation that a computer can do. But then this category of languages, or this hierarchy of languages, which is called the Chomsky hierarchy, again, Shubhrajit sir will be describing in detail, maybe in the next class or after that. Meanwhile, let's look at finite state machines or finite automata and what languages they can represent. Okay, so now let's look at the formalism of how the finite automata comes around. So what is an alphabet? Alphabet is any set of symbols. Okay, now for example, when we write text in English, we use an alphabet of 26 characters. Okay, A to Z. So these characters are nothing but symbols, particular symbols which are being used to represent the strings which are used in that language. Okay, so alphabet is nothing but a set of symbols or characters which make up the input strings. Okay, so string is a sequence of characters, but a string is defined on an alphabet. Okay, for example, if my alphabet consists of only the characters A and B, then I will look at strings consisting of only those two characters A and B, or 0, 1. For example, binary numbers are strings which are derived from the alphabet 0, 1. Okay, so 0, 1 is the set. Okay, as you can see at the bottom, and all binary strings are defined on that particular alphabet. So alphabet also formally it is defined by this character sigma, which you can see here. Okay, and strings are these characters of this alphabet appearing one after the other. Now, what is a language? Again, this term which I have been using for some time. A language is nothing but a collection of strings. Okay. So when we say a subset of sigma star, what is sigma star?
Ma'am, the set of strings, ma'am.
Sigma star denotes the set of strings. Yes, very good. Now remember, when we talk of strings, we also include something called an empty string, which has no characters. Okay, an empty string is typically represented by the symbol epsilon. These are some symbols which you have to become familiar with, because these symbols will be using again and again in this course. Okay, the sooner you get to understand what they are. So this capital sigma here, it typically represents alphabet. This epsilon represents an empty string which has no characters, but it is still a string. Okay, in C, for example, you would represent an this epsilon. How would you represent it? Two double quotes with nothing in between. Okay, so if you have these two double quotes, it is a string, but it is an empty string. Okay, so epsilon typically represents this empty string. And a language is a set of strings. Okay, just as an alphabet is a set of characters. Okay, a language is a set of strings. Again, these strings are defined on a particular alphabet. Okay, so sigma star, from sigma star, that means all possible strings which can be made up using the alphabets in sigma. A certain category, or a certain number of strings we collect and we make a set out of them, and we call this a particular language. Typically, a language is represented by this capital letter L. Okay, so for example, the set of strings of zeros and ones. So what does this mean? This means that the alphabet is equal to, so again, I would call it alphabet is equal to the set 0, 1. So alphabet here is 0, 1, okay, with no two consecutive ones. That means two ones must not appear in my string, okay, but zeros can appear. So you can see that if I started listing out the various strings which will appear in this particular language, let's first start with strings of length 0. So that is epsilon. Then we look at strings of length 1. So you would have 0, you would have 1. Okay, now let's look at strings of length 2. Okay, remember, no two consecutive ones. So 0, 0 is acceptable, 0, 1 is acceptable, 1, 0 is acceptable, but 1, 1 we cannot have. Okay, now let's look at strings of length 3. Okay, so 8 possible strings, out of which how many are acceptable? 0, 0, 0, 0, 0, 1, 0, 1, 0. 0, 1, 1 is not acceptable because two consecutive ones. Okay, 1, 0, 0, 1, 0, 1, 1, 1, 0 not acceptable, 1, 1, 1 not acceptable. Okay, now let's go to strings of length 4, and you can see these are the strings which are going to be, and this you can continue. So tell me how many such strings will be there in this language L?
Ma'am, an infinite number of
Yes,
strings.
infinite number of strings. An infinite number of strings will therefore appear in this language L. So language L, please note, this is an example of an infinite language. Okay, so language L can be a set, infinite set. It's an infinite set which can have infinite number of strings. So we have defined it. You can see how you can define. It's a set which we have defined in some English language description. So that is also possible. There are ways and ways in which you can define such sets. You can write a regular expression for this. You can write so many things. You might define this set in the form of a finite automata. Finite automata which accepts only those strings which will appear in this language. Okay, so this is let's say a regular language. This is a regular language. Okay, there's no doubt about it. And we can describe this using something called a regular expression, which we have not yet discussed. We'll be discussing that. But you can imagine that we can describe this using a finite automata also. A finite automata, therefore, describes such languages which have strings which conform to a certain regular pattern. That is why they are called regular languages. Okay, so language, you understand, a language is nothing but a collection of strings. Now these strings, you might constrain those strings to follow a particular pattern. Okay, in that case, if those a regular pattern, so that case it would be a regular language, and such regular languages you can accept using finite automata. Okay, I think I'm running out of time. We'll have another class now. So a deterministic finite automata, let's just look at the formal definition. A deterministic finite automata is defined by 5 things. So it is basically, they are defined by what is called a 5 tuple. It's a 5 tuple. Okay, so the constituents of the tuple are just this: Q, sigma, delta, Q0 and F. So this 5 tuple, what do you understand by a tuple first of all? What is a tuple?
Ma'am, a member of a like a member of a row or a column. That's all I know.
I'll give you a choice. Would you say a tuple is a set or a vector?
A
A
set.
vector.
Sector. I did not say sector.
Vector. Like
Vector.
collection.
Yes. Why vector? What is the difference between a vector and a set?
Ma'am, like how would I?
Ma'am,
I
set
don't
is
really
ordered.
order.
Yes,
So
order is
The
important.
ordered
In a
matrix.
set, the order does not matter. In a set, please note, unless it is a multi-set, a particular element will not appear more than once. Okay, if it's a member of a set, it is a member of a set. It does not have to appear again and again. Okay, but in a vector, the same element can appear in different positions. The order will make them different elements. Okay, so the order is important. If you change the order of the elements, then it will become a different vector. Okay, so a tuple is nothing but a vector, and this order is very important. I have written Q, sigma, delta because these are standard nomenclatures. If I put, instead of Q, if I wanted to write P, that will not make it different. Please remember, the order where I write it, the order, the place, value gives the meaning. Okay, so Q is typically used, so see, typically is written here. Q is typically used to define the set of states of the finite automata. For example, you have seen a finite automata with 3 states. So Q would have those 3 states, say Q0, Q1, Q2. Okay, the input alphabet for the strings which the finite automata is accepting, input alphabet you have to describe. Until you do that, you cannot describe a finite automata completely. Okay, transition function is the collection of transitions which we represent using the arcs. So what condition you will have an arc from which state to which state, that is what is given by the transition function, delta. Okay, small delta. Then start state, unless you tell which is the start state, again your automata is not completely specified. So Q0 typically is called the start state. And the set of final states, remember you can have more than one final state. You have already seen an example. Okay, so the set of final states, but the set of final states has to be a subset, okay, proper or otherwise, of Q. So you cannot get final states which are not existing in Q. So the set of final states. So if you final or accepting states, they also have to be specified. So all these 5 things, if you end up specifying, then you have completely specified your finite automata. If you specify your finite automata, that is one way of specifying a regular set. Okay, a regular set is nothing but a regular language, okay, which has strings of a regular pattern. So you have to give what are the input characters that comes in the input alphabet, okay. What are the possible states that the finite automata can go through? That is a set of states. What are the transitions? So in a picture, when we draw a finite automata, the moment we draw those circles, we have actually specified Q. Okay. The moment we put the arcs, we have specified delta. Okay. Of course, when we are specifying delta, we also specify the particular character on which that transition will take place, the input character. So we have specified the input characters, input alphabet. Okay. Then you remember I told you once that there will be one arc which is coming in from outside, and that will show the start state. Okay. So until you know where to start from, your finite automata is not completely specified. And of course, there will be some concentric circles which will tell us which are the final states of the finite automata. The final states or accepting states, because remember, in the general sense, a finite automata is nothing but a checker, okay, which checks various input strings to find out which are the strings which belong to the language for which it is defined. Okay, so it expresses a regular language and it is a checker for that language. So if you run a string through the finite automata, it's like a machine. An automaton basically is a machine, state machine. Okay, so it is a machine which automatically separates the strings which belong to the language which it will accept and the strings which do not belong to the language which it will reject. Okay, today I will stop here. Next class I will start again from this formal definition. So thank you very much. Next class is on Thursday and we'll be using this classroom. I'll set up a meeting. You can join here. And I'll also do one thing. I'll send you a team code so that you can all use that code and make yourselves member of this classroom. Is that clear?
Yes, ma'am.
Yes, ma'am. Thank you, ma'am.
So today we'll stop here. Thank you all for attending. And you may leave.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you, my dear.